We're going to focus tonight on liquefaction and in particular the impacts of liquefaction in the recent Christchurch earthquakes. Liquefaction is a very complex and phenomenon that practically changes the soil from a solid state into a liquid state over a very short period of time. We are literally talking few seconds. If the soils are loose, suddenly liquefaction is going to completely change the properties and behavior of soils. There are many ways to describe liquefaction, but I have one video which is really illustrative of this phenomenon. It was taken long ago in 1964 during the Niigata earthquake in Japan. A professional photographer happened to be at the airport just preparing for a takeoff when the earthquake started shaking, and he immediately started shooting the footage in front of the airport terminal building, capturing basically the occurrence of liquefaction around the building. It's a very short segment, and you will see that the quality is not so good. It is quite an old one, but it really shows the intensity and severity of this phenomenon quite well. So let's see what is happening around the building during the shaking and Niigata earthquake. So here is the building. This is the entrance, and you're seeing huge amount of water pouring out of the ground, literally in few seconds after the start of the earthquake. We are going to see some people now running out of the building shortly, and that will give you some indication about the speed and intensity of the phenomenon at the same time. So here is the water coming out, and the people are running out. And you can see the whole area has been flooded by water really in 5, 10, 15 seconds. This is the entrance of the building, and you can see that there was large settlement of the building. In approximately 2 minutes, the building settled 1 meter. It sunk into the ground. The settlement rate was 1 centimeter per second of that building. So obviously the soil completely lost the capacity to support the structure, and for that reason there was a very large settlement of the building. This is another view of Niigata after the earthquake. And Niigata earthquake is important because that was the first time liquefaction to be introduced to the engineering profession. The loss of bearings support caused sinking of buildings and even overturning of large 4-story apartment blocks. And there was other evidence of severe impacts of liquefaction on engineering structures. Liquefaction and its impacts have been present in recent earthquakes. Almost every strong earthquake is going to produce some amount of liquefaction, and it is going to affect certain structures. Even modern structures are affected. And this one here is a photo after the 1995 Kobe earthquake, again in Japan. This is a huge elevated highway. You can see some people here to the left and the bottom of the figure. The structure is about 40 meters high, tall. And due to lateral spreading and movement of the ground toward the river, there was collapse of the deck of the highway. To the right, you're seeing the Japanese Pride, the bullet train, which after 40 years of service, for the first time was derailed in 2004, again due to an earthquake and liquefaction effects. So designing against liquefaction is not that easy, and you really have to consider a range of factors in order to achieve the objectives that you have in the design. This is an aerial view of the Kobe Port Island, an artificial island, reclaimed land. You can see down to the right in the figure a lot of high-rise buildings, 20, 30-story buildings, and at the perimeter is the Kobe Port. To the left you can see a lot of orange and blue boxes, which are containers 12 meters long. So the size of the island shown here is approximately 500 meters by 500 meters. The color should be gray of asphalt, but the predominant color is here yellow, and that is the sand produced on the ground surface due to the liquefaction. This is how Port Island looked after that event, completely flooded, very similar to what we've got here in Christchurch on several occasions this year and last year. And there was clear evidence suggesting that the spurting of the ground was caused by very high pressures in the ground, and you could see evidence that those mud and water were going as high as a meter or maybe even more than that. I wouldn't like to go too much into scientific detail, but I think it's very important to understand what is the mechanism causing liquefaction. So I will try to explain it in simple terms, because that is going to really help us understand what we are seeing or what we saw here on the streets of Christchurch, and it will probably implicitly answer some of the questions. The first thing to realize is the structure of soils. So if we go and see the soils and sands in particular in a detail, and we are here seeing only 4 grains. Sand grains are very tiny, from 0.1 millimeter to 2 millimeters in diameter, okay? And what we will notice is that the contact area between the grains is very small. On the other hand, there is a lot of voids in between the particles. So sands can be loosely deposited or densely compacted. And the amount of voids in that structure is going to change significantly. If the soils are very loose, then the volume of voids is about the same as the volume of solids or particles. So you have lots of voids there. If the sands are very densely compacted, then 1/3 of the volume is going to be voids and 2/3 is going to be solids. And natural deposits exist between these states. Depending on the mode of deposition, if the soil was deposited by a river, then it is going to be typically in the range from loose to medium dense or dense deposit, depending on the time and the age of the soil. I'm going to discuss about that later on. So starting with this recognition that there is lots of void inside the soil structure, we can now analyze furthermore the conditions in the ground. If we look at this soil element here, which is located above the ground water table, the soil is going to be basically in a dry state, and the voids are filled with air. However, this element here, beneath the water table, the voids are going to be filled with water. So we say the soil is fully saturated. There is no air there, just water and particles. Now let's see what is going to happen to these 2 different soil types when shaken by an earthquake. So we'll go first with the dry soil. It has air there. And I'm going to just examine what is happening through one cycle. This is here showing the earthquake, where you have back and forth movement produced by the shaking. Okay? So let's see what is happening in only one cycle. As the seismic waves are propagating, they're going to deform the soil. So as the soil deforms, it has a tendency to densify. The volume of the voids is going to reduce. In the next cycle, the volume reduction is even bigger, and after a few cycles, you're getting significant densification or settlement, if you like, in the dry soil. If we consider what is happening in the soil that is fully saturated, things are a little bit different. In essence, it is still going to deform in the same way, but now it cannot densify because water is incompressible. So you're having the same sequence of deformation and the same tendency to densify the soil, but the water is not going to let it happen. Don't forget, this is all happening in few seconds, so there is no time for the water to immediately drain away. So after this sequence of shaking, what happens is in the dry soil, we are getting densification, whereas in the water-saturated soil, this densification is actually going to induce pressure in the water, because you want to densify the soil, but the water instead is going to increase the pressure inside. So we've started with some stable state. If we look what is happening at depth of 10 meters in the ground, we are having this water pressure, but we also have contact forces between particles. So all the weight of the soil sitting on top of this grain is going to produce this contact. However, once the earthquake is going to produce these excess pore water pressures, or the pressure in the groundwater, the pressure is going to increase to a point that it is going to separate the particles from contact. And at that point, liquefaction is going to develop. So the soil moves from a solid state and stable state into a sort of heavy liquid or viscous state, where it behaves in unstable manner, cannot support any more structures, and is going to deform hugely. If we look in this process, and I plot here the groundwater pressure as a function of the time, this groundwater pressure is going to reach the level where it will induce liquefaction in few seconds. We are literally saying 2 or 3 cycles. So this is cycle number 1, 2, 3 strong cycles are going to induce liquefaction in loose soil. Once it liquefies, so we've started before the earthquake from this state, where we have relatively loose state of the soil with a lot of water there, and the pressures in the water has increased to a point that the water pressure is separating the particles from contact, and we are getting some sort of suspension of particles and liquefaction produced over a few seconds. These pore pressures in the water are non-equilibrium pressures, so they will have to dissipate. Once we have them there, the water is going to start flowing towards the lower pressures. And usually we are going to find out what is happening is the water from large depth is flowing upward towards the ground surface. So this red line is slowly going down back to the original equilibrium state due to water flow and dissipation of pressures through that kind of water flow. Eventually, the grains are going to re-establish contacts, and the soil is going to re-solidify. At the end of this process, there is going to be some settlement of the ground. The largest problem is that once liquefaction is going to be triggered, the soil is unstable, it is going to deform a lot, both sideways and vertically, and heavy structures are going to sink in the ground, light structures and buoyant structures are going to be uplifted. We are going to see some illustration of this phenomena. Okay, so that is the background. Now, let's see what are the characteristics of Canterbury soils and Christchurch soils and compare with these factors and whether they are susceptible to liquefaction or not. The first thing to realize is that the Canterbury plains have abundant water supply, and you are well aware of that. And we are talking about surface, open channels, as well as a lot of groundwater supply. The second thing is the plains have been deposited by rivers, and they are comprised of very thick deposits, fluvial deposits. This is showing, for example, cross-section of the ground beneath Christchurch, covering the top 300 to 400 meters depth. And we are seeing layers of gravels interbedded with finer soils like clay, silts, creating structure where through the gravels there is water flow and supply through these aquifers, and that underground water is then discharged here at the sea. For liquefaction, the most important part is really the topsoil, about 20 meters thickness of the soil. And we are going to focus more on those features, on the features of those soils. But what is important to mention here is that underlying these soils, there is a so-called Riccarton gravel formation, which is an aquifer. So there are artesian pressures in that layer. That means pressures higher than what hydrostatic pressure is going to produce. That creates on its own some specific conditions disturbing the soils throughout the process of deposition, and also potentially inducing some unknown effects for even us during earthquakes. So let's examine now these top 20 meters. This is a cross-section cut through the soils of Christchurch in the east-west direction, aligning with the Beeley Avenue. So here is the Beeley Avenue, and then the cross-section goes up to the sea to the right, and to the left up to Rusley Road. At the top line there is showing ground elevation, and is basically suggesting that at Rusley, the ground is about 25 meters above sea level. At the CBD, it is about 5-6 meters above sea level. The next line, the blue line here, indicates the water table. It is basically suggesting that at CBD and to the east of CBD, the groundwater table is about 1 to 2 meters below the ground surface, so very shallow water table. So the soils to the east of CBD are well saturated. If you go to the west, then water table goes down to about 4 or 5 meters, depending where you are. And the last line there is indicating the top of the Riccarton gravel layer. So the yellow area is showing the thickness of the top alluvial soils, which are the most recent deposits and the most vulnerable to liquefaction. We can see that those soils are thick about 40 meters near the sea, about 20 meters beneath CBD, and about 10 meters at west of the city. Another important factor for the potential for liquefaction is the age of the soils. The younger the soils are, the higher the potential for liquefaction is. So this is a plot. On the horizontal axis, we've got the depth from the ground surface from 0 to 40 meters, and on the vertical axis is the age of the soils in 1,000 years. So from 0 to 10,000 years, we've got there years before present. The plot is suggesting that in the top 10 meters, the soils are mostly 4,000 years old or younger. In terms of liquefaction, these are soils vulnerable to liquefaction. Okay? You really need to have much older deposit in order to make them not susceptible to liquefaction. So this is another important feature suggesting that these soils are susceptible to liquefaction. Finally, the composition of these soils is also very important. Some soils are not liquefiable, like clays, for example, because clays, in addition to this frictional resistance, have cohesion, some sort of bonding between particles which is going to prevent liquefaction from developing. On the other hand, sands, gravels, and silts, or what we call granular soils, are liquefiable. The yellow band shown in these figures is indicating soil composition which is most susceptible to liquefaction. And the lines there are typical grain size distribution lines for Christchurch soils, and they are within the band. So grain size composition is also suggesting that the soils we've got are susceptible to liquefaction. So in summary, we've got fluvial deposits deposited by rivers in a relatively loose state that are highly saturated, of young age, and composition such that they are highly susceptible to liquefaction. Unfortunately, we've got all the important ingredients for liquefaction. So there wasn't any surprise. What was happening in the past during the last earthquakes was really just fortifying our understanding of this phenomenon and the predictions. Now, what is also important to mention and emphasize here is that these earthquakes produced extremely strong ground shaking, exceptionally high accelerations, very severe seismic loads, both on ground and structures. So we really have to put this at the top, because that was the reason why the consequences were so severe. Another very important point to mention is that there were a series of earthquakes, really 4 or 5 big events producing large or strong shaking, which is unprecedented, that a city was subjected over a short period of time to this many earthquakes producing very strong shaking. So in that sense, we were quite unfortunate and unique. Following the February earthquake, we went in the field and produced this preliminary map documenting liquefaction caused by the February earthquake. What you're seeing here is a result from a drive-through reconnaissance, driving through the city of Christchurch and identifying areas of very severe liquefaction, shown by red, areas of moderate liquefaction, shown by yellow, traces of liquefaction, shown by symbols, red dots, and blue lines are indicating areas where there wasn't visible evidence of liquefaction. The magenta is area where there was severe liquefaction, but it looked differently. It looked like the roads suffered very severe liquefaction, and it looked like the interaction between the native soil and the roads was kind of different there. And there was probably a lot of the roads acted like vents where most of these pressures were dissipated through the roads. There were a lot of cavities on the roads, a lot of collapses, and really a very severe distortion of road surfaces. Some of the properties were also affected, no question about it. But by and large, there was difference in performance there. That is why we've used different color. In our view, it is extremely important to discriminate between different areas and indicate the severity, because this is really pointing out specific features and weaknesses of the ground, if you like. So we should use this event to classify or characterize the ground the best we can. Now, a similar map was published in press after the February earthquake, and I've got many nice comments and few emails suggesting that, well, your map is not really showing exactly what was happening on our property. It wasn't intention to produce anything like that. This is really for general use, to understand global and general features and areas and how they responded in terms of liquefaction. And we certainly couldn't see what was happening on all properties at the back from the roads. So please take this with a grain of salt. If I go back and display the same plot here, and I'm going to superimpose on this the areas that liquefied during the September event. So those are the white contours shown there. And again, you can see that the weak spots along Avon River produced significant liquefaction in both events, and there are some differences that I will explain shortly. This is what happened in June, the 13th of June. Again, same areas pretty much liquefied, and the liquefaction was quite severe. I'm going to illustrate some of the severity or the effects of liquefaction through details, and especially the impacts on residential buildings, CBD buildings, as well as on lifelines, pipe networks in particular. This is another interesting comparison. As you are aware, there are about 15 strong motion stations recording these earthquakes within the boundaries of Christchurch City. For liquefaction, there are many factors affecting liquefaction, but for assessment of liquefaction, there are two features of the ground shaking that are the most important. One is the amplitude of shaking, and the second is the duration of shaking, or how many significant cycles of shaking the earthquake produced. If you combine these two into a single parameter, then you can compare the intensity of shaking between different events. Event with magnitude 7.1, like the September one, and the February earthquake, which was 6.3, because the duration of shaking, or the number of significant cycles, is well correlated with the magnitude of the earthquake. On the other hand, we do have records of the amplitudes through these strong motion stations. So if we examine the records in that way, the results are suggesting that for this yellow area, the 22nd February earthquake produced the strongest shaking, whereas on the green area, the September earthquake produced the strongest shaking. There is a band there without color, because we don't have information, and there is some sort of transition zone. Local effects within the certain zone may produce differences, but by and large, we are expecting to see dominance of the 22nd February earthquake in the yellow area, whereas the 4th September earthquake will be producing dominant shaking in the green area. And this is largely consistent with the observed liquefaction. Our colored map from the 22nd of February is pretty much under the yellow band, whereas some of the white areas where liquefaction developed during the 4th September earthquake is in the green zone. So now let's go and illustrate some of these liquefaction features in more detail. This is the view of Porritt Park from helicopter flyovers after the September earthquake and after the February earthquake. The amount of sand ejected on the surface is clearly suggesting very severe liquefaction. Okay? And you can see that in the February event, the amount of sand ejected doubled or even tripled, which is indicating that in both events there was very severe liquefaction. These are typical views in some of the suburbs. The volumes of sand on the streets was extreme. And in many of those cases, I would classify the liquefaction as extreme. And this is suggested by someone who has seen maybe 10 major events where liquefaction was a dominant feature. The ground response included also large vertical deformation and global subsidence, which is suggesting general weakness in terms of high or very thick deposits liquefying, and also initial density of the soils was probably quite low. So we are talking about loosely deposited soils. These kind of huge volumes of sand near houses, which are larger than the footprint of the building, clearly indicate thick deposits, maybe 3, 4, 5, 6, 7, 8 meters of the deposit have liquefied during this event. In principle, the amount of sand and the consequences of liquefaction that you are seeing on the surface are proportional to the thickness of the deposit that has liquefied and also to the severity. If you have very loose soil, the manifestation of liquefaction is going to be more dramatic. This is another property. To the left, we are seeing the whole property covered by mud and water after the September event, and to the right is after the cleanup. The mud and water mixture was approximately 40 centimeters thick, and in addition to that, the structure or the building itself settled and tilted. The settlement was in an additional 30-40 centimeters. So really huge movements. Quite often this is a cumulative movement due to 4 or 5 events. Many of these properties re-liquefied, and the total number of liquefaction times was 4 or 5 in some cases, which is quite unprecedented. This is how the property looked around, and this is one of the most artistic photographs related to liquefaction that I have seen. But it is not mine. A typical manifestation of liquefaction was differential or uneven settlement of structures and buildings in particular. And you can see one illustration here. If you look carefully here at the area of the contact between the two parts of the building, you're going to see damage to the building itself, which was caused by the differential movement. And quite often, this kind of movement in the foundations are going to create damage both to the foundation and to the building itself. Just another property, and probably you have seen this last week for a good reason. And this is how that area looked in June. It was really another event producing very large consequences of liquefaction, confirming that soils, when liquefy, they are not going to improve their characteristics in terms of liquefaction. They will be as weak as before, sometimes worse, sometimes a little bit better, but from a professional viewpoint, we are going to ignore that small possibility that they will get better. Usually that is not the case. And there is good reason why is that happening. One reason is that once the soils are going to liquefy and you are getting this suspension of particles in the water, they are going to re-establish contact based on due to the effect of gravitational forces. So the process is very similar to the process that actually created those deposits. So you're kind of going back in time, and now they are very fresh deposits, loosely deposited, and of course vulnerable to liquefaction. Lateral spreading is one of the most damaging forms or consequences of liquefaction. Typically it occurs on a sloping ground, and if the underlying soils liquefy, then obviously this even mild slope is going to drive the liquefied soil towards the open channels and waterways. This lateral movement due to spreading is quite large, from tens of centimeters, several meters, and even 10 meters or so. As we can see here at the back, as a consequence of this spreading, there is going to be usually some settlement of the ground, and many cracks and fissures are going to appear in the ground. All of these features are damaging for structures, so whatever is sitting there on these spreading soils is going to be subjected to very large deformations and forces. What we have seen here is some sort of block type of movement where a whole block of soil, about 100, 150, 200 meters long, moved together as a unit, and the largest cracks actually appeared at the end of this block, about 100 meters from the river. The reason for this could be, for example, that if there was an old river channel there, those soils have similar properties, and they do have tendency to move as a block. So at the end of that block, the largest cracks are going to be opening. And quite often, these cracks were running through residential properties and buildings. So here is a typical manifestation of lateral spreading. We can see a lot of cracks parallel to the river, and clearly we can see at the left bottom part of the figure sand ejecta, indicating that there was severe liquefaction in this area. The displacements are very large, and so are the cracks, and quite often they propagate in the residential area, and the close-up is showing us that quite significant fissures and 20, 30, 40 centimeters wide are running through houses. In some cases, the area affected by spreading was even 1 kilometer long, and about 200 meters from the river was moving towards the river by a magnitude of 2, 3, 4 meters. And you could see along that affected stretch very large fissures spread through the ground. At the back, the cracks were propagating through houses, and there was very severe damage. These openings and cracks are 1.5 meters wide, running through houses. Fortunately, New Zealand houses are very ductile, meaning they can deform a lot, but they're not going to collapse, and that saved a lot of lives. That is a very important feature, to accommodate a lot of deformation and movement without collapse. That is one of the tricks in the design, and in that sense, the residential houses in particular performed quite well, especially having in mind the exceptional forces and movements that they were subjected to. The damage was, of course, quite a different story. When these kind of very large ground movements are going to happen, the foundations are exposed to large forces, and quite often the ground beneath the foundation is going to be stretched, and this is causing a lot of damage, cracks within the foundations itself. Even the reinforcement of the foundations that is typically used in these houses was not good enough, because simply the level of forces was not anticipated in the design. So we can do better. This is one interpretation of the lateral spreading movements in the area of Darlington along Avon River, obtained by interpretation of aerial photographs, pre-event and post-event. By comparing these two sets of aerial photos, we can calculate what was the displacement induced by the earthquake. And for example, the red areas here are indicating areas where the movement was over 1 meter, or yellow ones are areas where the lateral movement was about 50 centimeters, and so on. So we can understand both the magnitude and spatial distribution of ground displacements. In addition to this aerial interpretation that was done by our Japanese colleagues, we have done conventional ground surveying, would go and do measurements along transects, one of these lines, for example, and we would measure the width of the cracks. And by superimposing the width of the cracks, you can actually back calculate what was the movement of the ground towards the waterway. Even more, we can calculate this kind of profiles where we've got here the ground displacement as a function of the distance from the waterway. So if we look at this orange line, which is coming at the top there, this is the displacement as a function of the distance, and we are finding out that the banks at that point move towards the river about 1.8 meters, and at a distance of about 100 meters from the river, the movement lateral displacement was about 0.4 meters. Any building or structure or pipe sitting within this 100 meters distance from the river was exposed to this kind of lateral displacement, between 0.4 meters and 1.8 meters. It is very difficult to accommodate in design that kind of magnitude of movement without damaging the structure or the facility. This is the water mains network of the city of Christchurch. We are working together with the Christchurch City Council and trying to improve the resilience of these systems, and by selecting the most appropriate materials, design details, and how to evaluate potential impacts of liquefaction. So this is the network, and the dots are now showing the locations of major failures caused by the 22nd February earthquake. And if I superimpose our liquefaction map, we are going to find out that most of the damage actually occurred in liquefied areas, which is not a surprise because the ground displacements were so large, and we are talking about buried pipes, so obviously ground is going to subject these systems to very large forces and consequent damage. The story around the wastewater network was the same and is even worse. Actually, this was probably the worst performing lifeline in Christchurch. This is the status of the network on 16th of March this year. The red color here indicates areas with no service, whereas the yellowish or brown lines are indicated limited service, and the green is full service area. Again, if we superimpose our map, we are getting very good agreement between the level of damage or performance of the system and areas that liquefied. Now, if we go and examine a little bit more in detail what is happening to all these buried structures, we will find out that liquefaction, or this pressure in the groundwater that was produced by the shaking, is going to produce additional pressure in the water, and this pressure increases with depth. So the largest pressure is going to be created at large depth, whereas the pressure of the water at the ground surface is going to be zero. For this reason, the water is going to flow upwards. Because the pressures are very high, during this flow, the water is going to take some of the soil, will find the weakest spot in the ground, the path of least resistance, and will bring the soil and the water on the ground surface. And this is how these sand volcanoes are actually created. The pressures are very large. Any buoyant structure is going to be uplifted on the ground surface. The surrounding soils are settling, whereas buoyant structures are going to be uplifted, and manholes are typically above the ground in many cases. This is what happened at Brooklands. This is what happened in Japan in other earthquakes. So my height is 170 centimeters. That is easy to spot, and this one is 180. This is the largest I have seen, and it is punching through asphalt. So it is really illustrating well what kind of high pressures are developing in liquefied soils. The larger the uplift is, basically it is suggesting that the liquefaction was deeper, so the pressures were higher. I have one small experiment which is illustrative of this phenomenon, and I hope that this is going to work. This is an experiment that I conduct with my students every year to illustrate liquefaction and how heavy structures are going to sink in the ground while light structures are going to be uplifted. I prepared this video just a few days before the February earthquake for LEARNS, which is an educational program for high school students. And what we've got here is a soil, sand, saturated with water, and on top of it is sitting one heavy structure, which is 3.7 kilograms in this case. And here we have a jar filled with water, about 800 grams, simulating some buoyant structure buried in the ground. And under static conditions, when there is no shaking, we can see that both structures are, of course, stable. Now, the whole container filled with water is placed on a small shaker, and this shaker is then used to induce small shaking to produce liquefaction and to see what will be the impact of liquefaction on these two structures. So here is just about the shaking to start. It is going to be a very slow shaking at the beginning because we are trying to induce gradually the liquefaction so that the effects are going to be clearer. So you can notice some small movement of the shaker. The amplitude of shaking is now increasing. Pore pressures are now developing in the ground. The water pressure is increasing and partially separating particles. We're going to see some instability here of the heavy structure, and it is gradually sinking, whereas the light structure will be uplifted. So this is the typical process causing settlement or sinking of heavy structures and uplift of light structures. So in the final part of the coverage of the damage induced by liquefaction, I'm going to mention a few things about our CBD buildings, and in particular how the foundations of high-rise buildings were affected by liquefaction. I will start with this view of the CBD and a map showing the streams within the CBD area as depicted in 1850s by the black maps. We found that this kind of history is quite important because it is pointing out towards areas where soils were loosely deposited and where we can find predominantly sand deposits that are liquefiable. This is not to say that all the lines that you are seeing here are going to coincide with the liquefied zones, because as I mentioned before, soils, and we have to go back to maybe 2,000–3,000 years of history in order to cover all the areas and recognize how this previous history is affecting the current state of the soils and how their susceptibility to liquefaction. Our detailed inspections are suggesting that there was a relatively severe liquefaction within this band, red band through the CBD, and there were certain zones where some features in the ground were really pronounced, indicating local collapses of the ground. One thing to realize is that the soils within CBD itself are highly variable. And what we have plotted here and represented is areas where the shallow top, let's say 10 meters of the deposits are dominated by different soil types. Then in the red zone that liquefied, we are having mostly silts and sands that are liquefiable. To the north of those, again, we get soft peat and soft silty soils. And if we cut a cross-section, this one is through Hereford Street, again we are seeing the variability of the soils, where we've got some sandy gravel deposit on the left and at the top, which is about 10 meters thick there, but then is thinning out, having only 3 meters thickness, and is disappearing at some part of the city. Underneath that layer is loose sand, and beneath that one is again much denser sand, so extremely variable soils, both vertically and horizontally. This profile here is very simplified. In essence, the soils are much more variable and there are much more layers and patches of different soils intermixed there. So the conditions, foundation conditions within CBD are extremely complex and challenging. This was creating situations where part of the foundation soils liquefied, and in those parts the settlement of the building was much larger than in the other parts of the building. So this is one typical example of deformation where the settlement is at the front part there. The lateral movement of the building is about 15 centimeters, and there is a tilt, residual tilt of about 2 degrees. In the same area, now the liquefied zone is to the left of the figure. We are getting very large settlement at that corner, which is about 26 centimeters relative to the other corner of the building. These kind of large and uneven settlements are inducing significant stresses in the structure and obviously are deforming and damaging the structure. There were buildings sitting close next to each other. They are on different foundations. This different depth of foundations is going to induce some sort of interaction between the buildings through the soil, and this in turn is going to affect their dynamic performance. It is difficult to anticipate the performance of these kind of buildings during strong earthquakes, and especially the interaction between the buildings. Quite often, not quite often, sometimes the buildings were on hybrid foundations. Part of the foundation will be shallow, the other part will be deep or piled foundation. And those are very difficult to design for dynamic loads. So it is not surprising that that kind of foundations didn't perform quite well. These are two profiles beneath the footprint of a single building, clearly telling you that the soils are very different beneath the same building. These soils are going to respond in a different way. Compressibility is different. Some of those are going to liquefy potentially, and this is going to obviously create some differential settlements and movements of the structure. This is a building on piled foundations. The piles are going quite deep, 14, 15 meters. So for that reason, the building itself didn't settle much. But the surrounding soils settled significantly, about 30 centimeters at that corner there, and on the other side, about 17 centimeters. The cars on the ground floor parking lot were all trapped because the building is supported by piles and have these very strong foundation beams here. Since it didn't settle, there was a differential movement of about 30 centimeters. This is, by the way, after the February earthquake. Now this has increased to 50 centimeters after the June event. Now this is a similar situation in the Kobe earthquake that I have mentioned. High-rise buildings, 30, 40 stories high, are founded on piled foundations. The piles are about 40 meters long. So the whole island basically settled 30, 40 centimeters, but the buildings didn't settle much. So we are having this kind of differential movement. And this was a common case where now the stairs, you're missing 2 or 3 stairs to enter the building. Those buildings are still there, they are in service, but they have few more stairs there. There are obviously many ways to improve the ground performance. One way is to densify the soil, because we know if it is very loose, then there is large potential for volume reduction. So if you densify the soil, you will eliminate the pore pressure buildup. Another is to solidify the ground, to inject cement or other binding agents which are going to improve both the strength and reduce deformability. Building walls inside the soil is also going to reduce the deformability. If you reduce the deformation, then basically there is no tendency for volume change. So this is one way of addressing these issues. This is why we've got those talks about building the walls. Is in essence reducing the deformability of the soil, and that is going to reduce the pore pressures in the ground during earthquakes. Another approach is to use drains and dissipate pore water pressure. I'm skeptical about that method, because if we are agreeing that pore pressure is going to develop in 5 seconds, How much water you can take with drains in 5 seconds? Not much. Drains will work for moderate earthquakes, but they won't work for strong earthquakes. Finally, in addition, you should design foundations that are going to be robust, will be tied together well, will work as a unit, and will reduce the deformability of the superstructure. Quite often, actually, you have to use a combination of measures. The methodology is there, the technologies are there, but they are costly. They all come with some cost. In essence, those costs are something to consider, including the construction time and what is your performance objective. What is acceptable from our viewpoint? It's not us as engineers, but us as a community. What is an acceptable performance for a building or a city during a strong earthquake? That is the debate that we should have. Because what these earthquakes are pointing out is that while we have solutions for individual buildings, we are not considering the city as a system. We have to start thinking of this as a system, and we need to have criteria for individual performance and criteria for a system performance. Otherwise, it will be difficult to address the issues around the resilience of systems and the city as a system. This is very complex, so don't even try to understand what's going on there, but I will use it to illustrate only 1 or 2 points. The process in the design is basically to consider the conditions of the ground and the conditions of the structure and potential earthquakes, and to see how those earthquakes are going to influence the ground and the structure and what kind of damage is going to result from these events. So you can do this in this way. For example, for Christchurch, you can consider some local earthquakes, like the one produced in February. You can consider some earthquakes produced by faults in the Canterbury plains, like the one produced in September. And then we have the Alpine fault, which is a significant source of earthquakes. And we've got maybe the Hope fault, which is another significant source. So we have 4 sources. We've got an earthquake in September. We've got another one in February, and a couple of those in June. This is unprecedented that we've got 4 events out of these sources within 1 year, and all produced exceptionally high ground motions. So the whole point of the design is to understand what will be the impact of each of these earthquakes on particular structure, whether that is a residential building, a high-rise building, or water network. And by using the previous methodology that I was suggesting, where you can use the magnitude and the amplitude to compare different events, we can calculate and see what kind of ground shaking the Alpine fault is going to produce and compare it with the September and the February earthquakes. So if this is on the vertical scale, we have a measure for the severity of shaking or the liquefaction induced. This is specific to CBD. Then the green band is showing the range of or the severity of shaking produced by the September earthquake. The yellow one is the February earthquake, and the blue one is a predicted one for the Alpine fault event. This is suggesting that the Alpine fault event, even though will produce very large magnitude 8 earthquakes, since it is far away, the impact is going to be less or similar to the September event in terms of liquefaction, and it will be less than the February event, which is good news. We have to understand that the ground conditions and the foundation conditions in Christchurch are exceptionally complex, and that we've got a series, multiple events producing very strong shaking and affecting a number of structures, well designed in my view, but really subjecting those to a series of earthquakes producing quite large damage in each event, as well as significant cumulative damage. Liquefaction was one of the major culprits to the damage and affecting residential buildings, CBD buildings, as well as pipe networks. It also affected the natural environment. We do have global subsidence in some areas, which is now increasing the exposure to other hazards like flooding. There are many methods and technologies available to address these issues, and they can be better and will cost more, or will be cheaper and you will achieve only certain level of improvement. So we have to decide what is our objective for the performance of individual structures as well as the system. This is of critical significance. We have to have a common view as a community. Is it acceptable to have your central business district affected by an earthquake and out of use for 1 year or 2 years? It might be acceptable, but this is something that we never taught in the profession in terms of designing systems. These earthquakes are certainly pointing out to the need to do something like that. And finally, when we are discussing relocations and going somewhere else, we should not forget that liquefaction is only one of the hazards. So you have always to compare it with the other hazard and what does it mean for your performance of objectives. I will summarize at the end our activities. We have conducted about 200 tests on residential properties, and I'm quite sure we have bothered many of you. We are using this specific test, Swedish weight sounding test, for the first time in New Zealand. It is a simple portable test where you can probe the quality of the soil up to 9 meters depth and identify whether liquefaction is an issue or not. We have measured lateral spreading at about 150 transects throughout the city of Christchurch and Kaipoi, and have inspected about 500 houses specifically to understand the impacts of spreading and liquefaction on residential houses typical for New Zealand. We are currently investigating about 160 houses and specifically trying to understand how the 4 most typical foundation types used for those buildings performed, so that we can improve our current practice and design. We are trying to do something similar for bridges, pipe networks, and we are working hard in the CBD trying to understand the performance of foundations of high-rise buildings. Just last week, we've started collecting undisturbed samples from the CBD soils up to 10 meters depth by using a new methodology to pull out the samples out of the ground without disturbing them, to have the same density and structure of the soil, to transport them in the laboratory and test them so that we get extremely high quality information about the strength and seismic performance of these soils. Of course, you cannot do this alone, and I have a fantastic group of students that are working with me. This was a really national and international effort with a lot of support coming from the United States and Japan. And working together, we are continuing our work, and I'm quite sure that we are going to produce results which are going to be fruitful not only to Christchurch, but the whole of New Zealand and internationally as well. And at the end, after the September earthquake, I've decided to put a bid to host the next conference on earthquake geotechnical engineering, where liquefaction is a major feature. And that was presented at the conference in Santiago in January, and we won the bid. So we will host the next one in 2015. Thank you.